My name is Dr. KCH Apparao, working as Associate Professor in Mechanical Engineering Department. Today, I would like to explain about the uh, discussions on question bank mainly just long answer questions. You will see what are the important questions which are included in the first chapter, that is mode of heat transfers. You'll see some frequent questions, very important questions. Okay. So first one, we'll see briefly explain the laws of heat transfer and give importance in quantitative analysis. You know that heat transfer, heat is the form of energy. Heat transfer is the energy in transit, or so transmission of energy from one object to one body to another body, or one substance to another substance. That is heat energy, heat transfer. Okay, the rate of heat transfer, it is represented by Q watts. You know that units of this one. So this heat transfer takes place in three types of modes. You know this one. The first one is the conduction. Second one is the convection. Third one is the radiation. So we already explained in previous classes also. You know that conduction occurs only in solids. Conduction occurs by two types of phenomena. One is the lattice vibration, another one is the movement of free electrons. Here, conduction only takes place by the vibration of the particles, not movement of the particles. You know this one. Okay. So similarly, convection, here we'll see the movement of particles from one place to another place. So it is convection is completely associated with the movement of particles. Conduction is completely associated with the movement of free electrons or vibration of the particles. You know this one. Okay. Radiation, here no need of any medium. Without the medium, heat transfer takes place by uh, through the phenomena of electromagnetic wave phenomena. You know this one. Okay. So to find the rate of heat transfer Q through conduction, through convection, through radiation, some laws will be given by different persons, experts, scientists. The first one, the conduction. So the rate of heat transfer through conduction is measured by Fourier's law. That is, to explain the mathematical uh, calculations of values. So there is one law, that is Fourier's law. You know this one. Okay. Fourier's law. So that is called. So by the help of the Fourier's law, we can measure the rate of heat transfer uh, in conduction process. Similarly, convection, to measure the rate of heat transfer Q through convection process, there is one law, that is Newton's cooling law. Newton's cooling law. Okay. So similarly, to measure the rate of heat transfer Q by radiation process, so that is by Stephen Boltzmann. So Stephen Boltzmann law. Okay. So mainly there are three laws to explain or to measure the mathematical values or quantitative values of the heat transfer in three modes. That is, the first one is the Fourier's law, second one is the Newton's cooling law, third one is the Stephen Boltzmann law. Okay. So according to Fourier's law, the rate of heat transfer is directly proportional to the area of the, just like suppose this is a homogeneous body, area of this one, the rate of heat transfer Q is directly proportional to the area which is normal to the direction of heat flow, which is normal to the direction of heat flow. So that is the first condition. And this rate of heat transfer is directly proportional to the temperature gradient. Temperature gradient means, suppose the body of temperature, this is the T1, this one is the T2. Okay, so in x direction, so thickness you can consider this is the dx in x direction. Then dt by dx, this is nothing but temperature gradient. So this q rate of heat transfer also directly proportional to dt by dx. Okay, so according to Fourier's law, this rate of heat transfer is directly proportional to the area of the homogeneous body which is normal to the direction of heat flow, and this rate of heat transfer is directly proportional to temperature gradient. Okay, so based upon this one, he has given one formula, that is q is directly proportional to minus ka dt by is equal to. Okay, so we'll remove the proportionality and we'll give equality. So by using some constant, that is the k, that is nothing but k is nothing but thermal conductivity. You know this one, thermal conductivity. So minus symbol shows the temperature always transfer from higher to lower. So just temperature gradient is always decreasing order. So we'll use this one minus. This is the formula. Okay, to measure the quantitative measurement of rate of heat transfer by conduction process, this is the formula, minus Ka dt by dx. So K is the thermal conductivity, area is the homogeneous body, area of the homogeneous body, and mm, dt by dx is the temperature gradient. So temperature difference with respect to direction. So this is the Fourier's law. Okay, so that is the first law. Now we'll see second one, that is related to convection. So to explain the, or to measure the quantitative value of rate of heat transfer q uh, through convection process, there is one law that is called Newton's cooling law. So according to this Newton's cooling law, he has given q is equal to HA into delta T. Delta T is nothing but temperature difference. So Ts minus Tf. Okay. Suppose there is a one surface, the fluid is flowing like this one. So the fluid is flowing like this one. So this is the temperature of the surface Ts. This is the fluid temperature Tf. So if the Ts is greater than Tf, automatically heat transfer takes place from the solid body to fluid. Okay. So H is the heat transfer coefficient. A is the area of the surface. So based upon this parameter, he has given just one formula, that is Q is equal to HA into delta T. So by using this formula, you can find out the rate of heat transfer in through convection process. Okay. So this is the law which is related to convection process. Now we'll see. Uh, the law which is used to measure the rate of heat transfer through in radiation process. So that is called Stephen Boltzmann law. According to Stephen Boltzmann law, so the rate of heat transfer Q is directly proportional to fourth power of the absolute temperature of body, any body. Okay, so just like here there is no medium. uh, so suppose if the big body and the small objects, here in this case we neglect the areas and we will take this formula. Suppose this is the sun, this is the moon. Okay, so the areas are very big, there's no need to consider this one. In this case we can take this formula, q is equal to, we remove this proportionality and we will give the constant, that is called Stephen Boltzmann constant, sigma into t to the power of 4. The value of sigma is equal to 5.67 into 10 to the power of minus 8 watt per meter square Kelvin to the power of 4. So this is the value. Okay, suppose there are two bodies if the heat transfer takes place between black body and some gray body, so both are at same area. So this is the another body. Okay. So the temperature is equal to T1, temperature is equal to T2. So heat transfer takes place between these two plates by the help of radiation process, because there is no any medium between these two bodies. If you assume this one, then the area, if you consider the area both the plates are same, A, and then emissivity, then you can consider emissivity, ability to transfer the rate of heat transfer through radiation process. Okay. This is if you consider this emissivity, then the formula will be like this one. Here also some view factor also you can consider. View factor is the depend upon the geometrical position of the plates. Okay. So that is represented by F, this one. So then if you consider all this area, emissivity and the view factor or shape factor, then the formula will be like this one according to Stephen Boltzmann law. Q is equal to FA into epsilon into T1 to the power of 4 minus T2 to the power of 4. T to the power of 4. So this is the final formula. So these are the three laws which are related to modes of heat transfer to measure the mathematical or quantitative values of Q, rate of heat transfer, through conduction, through convection, and through radiation. So this is the just details regarding the laws of heat transfer. Okay, you can see like this one. Next we will see here in thermal conductivity, in conduction process, that is a Fourier's law. We saw one constant that is called K. So according to Fourier's law, Q is equal to minus Ka into dt by dx. Okay. So this K is nothing but thermal conductivity. We'll see what is the importance of the thermal conductivity. So thermal conductivity is the ability of material to conduct heat. To conduct heat. So it is the property of material. So some materials have high thermal conductivity, some have less conductivity. So mostly metals have high thermal conductivity, because in the metals they have the free electrons, ocean of free electrons, and so due to this ocean of free electrons, uh, heat transfer takes place from uh, one place to another place of the same object. So that is called thermal conductivity. So thermal conductivity is represented by K. It is measured of ability of the material to conduct heat. So here thermal conductivity of water is very less. Mostly metals have high thermal conductivity. Solids, in which metals have high thermal conductivities, and fluids have very low conductivity. So K water, thermal conductivity of water is equal to 0.608 kilojoule per kg Kelvin. But in case of iron, thermal conductivity of iron is equal to 80.02 kilojoule per kg Kelvin. Okay. So iron can conduct heat more than 100 times faster than the water. So that is the ability of metals to conduct heat or to conduct electrical power also. Okay. Thermal conductivity K. So we can define like this one: rate of heat transfer through unit thickness of material per unit area per unit temperature difference. Unit thickness, unit area per unit temperature difference. That is called thermal conductivity. So it depends on physical structure of materials. Okay. Structure of materials and atoms and molecules. The three in the solids, atoms are very tightly packed, very closely packed and tightly packed. So like this one, due to vibration, the thermal conductivity or heat transfer takes place. Or due to the passing of free electron from one region to another region, heat transfer takes place. So but in case of fluids, the molecules are very the distance between the molecules are very high. There is no vibration. between this, and they don't have the free electrons to carry the heat transfer. So this is the phenomenon. So thermal conductivity is depend upon the physical structure of the material and the atoms and molecules, which depends on the state of matter. Okay. So there are some materials are given which have high thermal conductivity. Diamond, okay, 2300, silver 430, copper is the 400, gold is the 315, and aluminum 235. So the iron is the 80. Okay. So these are the good conductors. Here we can see the bad conductors. We can say those are called as insulating materials. Brick is the 0.7. It is solid, but these non-metallic non-metals, those don't have the free electrons. So conductivity is very less. That is very less, very very less. Those metals, those solids are called, those non-metallic solids are called insulating materials. So brick is the insulating material. Water, the the conductivity of water is very very less. Wood also 0.18, helium 0.15, and rubber is the 13. Okay. So here you can see thermal conductivity ranges very less for glasses, next to liquids, next to insulators, next to non-metallic solids. Okay. Next alloys, next to pure alloys, next to non-metallic crystals. Okay. So non-metallic crystals have high thermal conductivity. So this is the graph. You can observe the conductivity property on different materials. Okay. So this is the explanation regarding the thermal conductivity. So not resistance, thermal conductivity. Explanation regarding the thermal conductivity. Conductivity. Okay. So now we'll see. Now we'll see thermal resistance. Now we'll see importance of the concept of thermal resistance, and what parameters resistance depend upon. Resistance is equal to Q. We can say resistance is equal to, suppose Q is equal to temperature difference delta T by R thermal. So this R thermal is nothing but thermal resistance. So it means thermal resistance is equal to temperature difference by Q, rate of heat transfer. Okay. The ratio between the temperature drop and the average heat from across an interface, okay, when two objects are in contact. It means temperature difference by rate of heat transfer. That is called thermal resistance. Thermal resistance. We can see according to, we can understand the electrical analog formula. Suppose this is the one homogeneous body. This is the temperature T1 and T2. Temperature is flowing like this one. This is the rate of heat transfer Q. Area A. This is the area A. And the thickness of this metal is equal to, suppose, L. Okay. Here, just you can see the rate of heat transfer is equal to thermal resistance is equal to, you can see, according to the formula of Fourier's law, Q is equal to minus Ka into dt by dx. So minus K is the thermal conductivity of the material, area A of the homogeneous body, delta T, the T2 minus T1 by thickness is equal to L. Okay. So minus minus, it means Ka into T1 minus T2 by L. Okay. You can bring this one to here. Then you can rewrite like this one, T1 minus T2 by L by Ka. So is equal to Q. Okay. So then is equal to Q. So then you can write like this one, L by Ka is equal to T1 minus T2 by Q. So this L by Ka is nothing but the thermal resistance of this body. Thermal resistance of this body. Okay. It is represented by RTH. Okay. So RTH is equal to T1 minus T2 by Q. Temperature difference by rate of heat transfer. That is called uh, thermal resistance. Suppose if there are more bodies, some layers of slabs, rectangular slabs. Suppose you will see, we can read it like this one, the same formula based upon the electrical analog formula. So this is the temperature T1, thermal resistance is equal to like this one. This is the temperature T2. So temperature T1 and temperature T2, this is the RTH. This shows the rate of heat transfer is uniform. Then the formula Q is equal to temperature difference T1 minus T2 by RTH. Okay, RTH. So this is the formula. Suppose many layers are there, we can add another layer. Okay, like this one. Then RTH is equal to R1 plus R2. R1 is equal to L1 by K1A, A1 plus L2 by K2A2. Okay, so according to previous formula. So in this way, this shows the thermal resistance. The parameters, what are the parameters depends upon means you can see thermal resistance RTH is depend upon the area. Okay, so according to this formula, Q is equal to T1 minus T2 by L1 by Ka. Okay, so this is called thermal resistance. Thermal resistance depend upon the length, thickness of the body, thermal conductivity of the body, area of the body. So all these things it will depend. So RTH is equal to this depend upon the thickness and the thermal conductivity and the areas. Okay. So this is the concept of thermal resistance. Now we'll see another important question. Next question we'll see. Why metals are good thermal conductors? Why non-metals are pure conductors of heat? Explain with examples. We know that conduction takes place only in solids, but only in metals, because in metals, the metals have ocean of free electrons. Ocean of free electrons. So this is the atoms. The free electrons are here. Free electrons are here. Free electrons are here. Free electrons. So these free electrons move from one place to another place. These free electron carries the heat from one particle to another particles. So it occurs only in metals. So because metals have free electrons, those free electron carries the rate of heat transfer, heat energy from one particle to another particle, one region to another region. Okay. But in non-metallic conductors means insulating materials. So those are the solids, but those particles doesn't have any free electrons. So due to this one, heat doesn't transfer from one particle to another particle. So because of this one, those solid non-metallic objects act as the insulating materials. You can see many here already. The given the example of those uh, poor conductors and good conductors here. So these are the good conductor materials. These are the poor conducting materials: diamond, silver, copper, gold, aluminum, iron. So these are the good conductors. So because these metals have free of electrons or ocean of free electrons. So due to the movement or carrying of energy through those electrons, heat transfer takes place. Here, these are the solids, but non-metallic objects, though they don't have the free electrons. Because of that one, heat transfer doesn't takes place. So you can observe this one. These are the examples. So in metals means their electrons are tightly bound to their atoms. electrons are tightly bound to their atoms and cannot move around freely. So that is called non-metallic non-metallic condition. Non-metallic condition, electrons are tightly bound to the free electrons atoms. They have the free electrons but tightly bounded to the atoms. So they have electrons but those are not free electrons. Okay. So due to this bounding, they cannot move. They cannot freely move from one place to another place. So therefore, when heat is applied to non-metal, the heat energy has to be transferred from atom to atom by lattice vibration. Here lattice vibration is also very less. Okay. So this process is much slower than the movement of free electrons. Because of movement of free electrons, heat transfer takes place. Okay, so those non-metals act as a poor conductors because of this reason. So, but metals have sea of free electrons, so those carries the heat energy. Okay. Next, way explain the concept of overall heat transfer coefficient. Overall heat transfer coefficient. According to convection, we know this one Q is equal to HA into delta T. HA into delta T means T solid minus TF. Okay. H is the heat transfer coefficient. H is nothing but heat transfer coefficient. So here we are seeing the overall heat transfer coefficient. Overall heat transfer coefficient. So this is only some one body. If it is one body, we can consider H. It has only H in the solid to solid. So H is the heat transfer coefficient. If you consider the heat transfer takes place from some more layers. From this is the layer 1, layer 2 and layer 3. Okay. So this is the temperature T1, T2, T3 and T4. So like this one. Area A1, A2 and A3. Okay. So this is the condition. So here heat transfer coefficient is different. Here also different. Okay. So if you consider this one, the suppose heat is transferred from atmosphere hot to fluid to solid. So that is the temperature of hot fluid, THI inner. Uh, this is the cold fluid. Suppose atmospheric temperature, that is the TF. Okay. So here heat transfer coefficient is different. H hot fluid, HF. Here H cold fluid, HCF. So different types of heat transfer coefficients are placed. Just for finding this heat transfer, overall heat transfer in this system, you have to consider all the heat transfers. That is called overall heat transfer coefficient. You can find out the overall heat transfer coefficient. Okay. So that is the overall heat transfer coefficient. Overall heat transfer coefficient is nothing but 1 by sigma r. 1 by sigma r. You know this one, thermal resistance. So if you know the overall thermal resistance, then you can find out the overall heat transfer coefficient also. Here you can see the overall heat transfer coefficient is defined in terms of total thermal resistance between two fluids. Okay. So this is U is equal to 1 by sigma r. If you know the thermal resistance, then 1 by sigma r is nothing but overall heat transfer coefficient. So how to find the total thermal resistance, already explained in previous slide. You can refer this one. Okay. This is the formula to find the overall heat transfer coefficient. Okay. So next to differentiate between the steady state and transient heat conduction. Transient is nothing but unsteady state condition. Steady state means suppose in the system the temperature difference doesn't takes place with respect to time. It means temperature difference dt by d small t is equal to 0. That is called steady state condition. Okay. If the temperature difference is changes with respect to time to time, okay, so that is not equal to 0. That is called transient heat conduction, unsteady state condition. So every system starts with the unsteady state condition, that then it reaches to steady state condition. If you just, for example, the measuring of body temperature, just will put the thermometer in our mouth, it starts with unsteady state condition. It means the temperature levels will be changes with time to time. Up to certain time, it will stop. It means beyond that reading, it will not rise. So the system means that starts with the unsteady state condition that reaches to steady state condition. Unsteady state conditions are uh, precursors to steady state conditions. Precursors to the steady state condition. No system exists initially under steady state condition. You start with unsteady state, then reaches to steady state condition. So sometimes must pass after heat transfer is initiated before the system reaches to steady state. During that period of transition, the system is under unsteady state condition. Okay, so this is the main difference between the steady state and unsteady state condition. Okay. Next, describe the different types of boundary conditions applied to heat conditions. Boundary conditions are very important to find the heat transfer rates between two temperatures like this one. Okay, there are two types: initial conditions and boundary conditions. The need of general differential equation describe the generalized principle. Here, those were T by dou T. So, so this type of double type uh, differential equations, those have two types of the boundary condition. Here you can observe this one is the temperature T1, this is the temperature T2. The boundary condition here is equal to, suppose this is the distance x, if it x is equal to 0, it is x is equal to some L. Okay, at x is equal to 0, at x is equal to 0, the temperature is equal to 60 degrees here, 60 degrees. At x is equal to L, temperature is equal to 20 degrees. So based upon these two boundary conditions, you can find out this rate of heat transfer. Okay, so the T relationship, that is called minus 7x plus 60. So internal conditions, conditions and the boundary conditions provide unique solution. Okay. Next, how many internal conditions and boundary conditions do we need for completely defining the problem? Okay. The number of ICs and VCs in the direction of each independent variable of a problem is equal to order of highest derivative of the GDA. Here, uh, two derivatives and one derivatives, two derivatives and three derivatives. Here, this is the one derivatives, dou t single derivative. Dou t by dou small t. It means only one uh, conditions, internal conditions. Here two boundary conditions. Here also two boundary conditions. Here also two boundary conditions. Here two boundary conditions. Here two boundary conditions. This here one boundary condition. So this is the number of boundary conditions which are depend upon the uh, general differential equations. Okay. So does any of the energy of the sun reach the earth by conduction and convection? Okay. Conduction and convection, already discussed this one. In conduction convection, medium should be needed. In conduction, occurs by the help of the lattice vibration and free electrons of the movements. Okay. In convection occurs free electrons of the particles from one place to another place. But in radiation, no need of any medium. Okay. If you compare this one, sun and the moon, there is no medium between the sun and moon, that is vacuum. So because of that one, so conduction principle or convection principle is not applicable here, but heat transfer takes place by the help of the radiation. So that is the phenomena of electromagnetic wave phenomena. Okay, so you can understand this concept. You know that radiation concept. Deriving the general conduction equation. Already in previous classes I explained this one. The final equation for this one, dou square t by dou x square plus dou square t by dou y square plus d square t by dz square plus q by k is equal to rho cp, if you rho cp by k into dt by d small t. Okay, this one is already derived in previous class. Okay, so if you consider energy increasing energy is negligible, then the formula is delta t square is equal to like this one, rho rho cp by k. You can write like this one. This is alpha 1 by alpha. 1 by alpha is nothing but diffusivity. Diffusivity is equal to k by rho cp. You know this one. In previous classes also I explained this one. 1 by alpha into dt by d small t. Okay. If you consider this is the steady state condition, automatically it will be 0. Okay, then del square is equal to 0. It means d square t by dx square plus d square t by dy square plus d square t by dz square, okay, is equal to 0. So we already explained previous class, you can refer this one. Okay, so next list out some examples of natural convection, forced convection. Natural convection occurs by the buoyancy effect, free electron movements from bottom to top due to the buoyancy effect, because less heat, when you gives the heat to these particles, the less density part, it means heated particles, density of the heated particle will be reduced. This less density particles moves upward, and heavy density particles moves into downward direction. In this way, the heat transfer takes place, the movement of the particles. So this movement of particles occurs naturally, that is called natural convection. If the movement of the particles occurs by some external agent, that is called forced convection. So these are the examples of natural convection. So all these things, you know this one. Okay, here. So examples of the natural convection. This one also based upon the natural convection principle, it will works. Okay. So thank you. These are the different books, you can refer this one. Thank you listening this class. We'll see different formulas, different problems or problem solvings on this mode in next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.